Okay, these are the solutions for the Unit 2 practice test. Question number 1, we need to find the intervals where the function's increasing or decreasing. That means we need the first derivative and then set it equal to 0. This is from Chapter 3, Section 3.1. So the function's in the form of a quotient, so we need to use a quotient rule. So the quotient rule is low times d high minus high times d low all over low squared. Now we can simplify and combine like terms in the numerator. We're going to have 25x squared plus 625 minus 50x squared and there's our denominator. We can combine those two like terms there to get negative 25x squared in the numerator. Now, when we're finding critical numbers, remember there's two ways we can find either the first derivative equals 0 or the first derivative is undefined. Now, to figure out where a function like this is undefined, we look at the denominator, because remember the denominator can't equal 0. But there's no values of x that's going to make this denominator equal 0, because anything I plug right here in for x, I'm going to square it, which makes it positive. And then I add 25, so it's positive still, and then I square it here. So no matter if x is positive or negative or even 0, whatever I plug in for x right here in the denominator, it's always going to come out to be something positive. So it's never going to be undefined. To figure out where a rational function equals 0, we talked about this in class, you need to worry about when the numerator equals 0. So that's the equation right there that we need to solve. Is negative 25x squared plus 625 equals 0. So if you subtract the 625 over, divide by negative 25, you're going to end up with x squared equals 25. So the two critical numbers are x equals plus or minus 5. So as we've done many times here in Chapter 3, we put the critical numbers on a number line and test some test points like 0, negative 6, positive 6. We could test those test points. So if I plug in a negative 6 right here for x and then run it through that equation, we'd end up with a negative value. If I plug in a 0 right here for that equation and for x, you'd end up with a positive value. And if you plug in a 6 right there for that x, you would end up with a negative value. So remember the negative value here denotes that any number in this interval, so that's from negative infinity all the way to negative 5, because of that minus sign above it, that indicates that the function is decreasing. So we would say the intervals of decrease are negative infinity to negative 5 and from 5 to infinity. And the intervals of increase would be this interval right here where we have a positive sign. So that interval is from -5 to 5. Okay, finding points of extrema, the relative min and the relative max. Very similar to question number 1. Question number 2 comes from section 3.2. We need to find the first derivative. And we set the first derivative equal to 0. We can factor out a -3. And then factor that quadratic expression. So we end up with two critical numbers, x equals 3 and x equals 1. So first derivative test, we need to choose some test values. So we could test 0, we could test a +2, test a +4. If I plug in a 0 here and there for both of those x's, we're going to get 0 minus 3, that's negative, 0 minus 1, that's negative. But a negative times a negative would be a positive. However, we have this -3 out front. There's a negative there that we need to account for. So let's try that again. If I plug in a 0 for that x and a 0 for that x, I get a negative times a negative, but then when I times it by that negative, we get 3 negatives, so that interval there is negative. Now if I plug in a 2 for that x and for that x, 2 minus 3 is negative, but 2 minus 1 is positive. So we have a negative times a positive there, which gives us a positive value. If I plug in a 4, 4 minus 3 is positive, 4 minus 1 is positive, but when you multiply it by that negative, then it's negative. So we have a negative or a decreasing part of the function, and then it switches to increasing right there at x equals 1. So that indicates that x equals 1 is a minimum. So there's a relative minimum when x equals 1. So if we go back up to the original function and plug in a 1 for all of those x's, we're going to have -1 plus 6 minus 9 plus 4. So that's -1 plus 6, that's 5. 5 minus 9 is -4 plus 4. That's going to give us a 0. So -1 comma 0 is relative min. Relative max, see here, this interval means the function's increasing, so the function's increasing and then it switches to decreasing when x equals 3, so that's our relative max. And if we plug in a 3 for all the x's, 3 cubed multiplied by negative, so that's -27. 3 squared is 9 times 6, that's 54, so that's 27. 27 minus 9 times 3 is 0 plus 4, so we're going to have a positive 4. Okay, this is also from section 3.2, absolute, minimum, and maximum. Those are found a little bit differently. It starts the same. We need to find the first derivative. We still have to set it equal to 0. So now 3 doesn't go into all three of the terms. So we're going to have to factor using factoring by grouping. So we multiply the first number and the last number there. 3 times 16 is 48. So we need factors of 48 that add to 16. So that's going to be a 12 and a 4. 12 times 4 is 48, and 12 plus 4 is 16. So what needs to happen is we split this middle term up into those two values. So 3x squared plus 12x plus 4x plus 16, and we group the first two terms. Group the last two terms. From this first grouping, we can factor out a 3x. From the next group, you can factor out a 4. And because both of those match, that makes it a common factor. So if you factor out the x plus 4, that leaves 3x plus 4. So we have two values to consider. X equals -4 and x equals -4/3. Now, they tell us specifically that the absolute minimum or maximum needs to occur within this interval -5 to -3. -4/3 doesn't fit within that interval, so we don't consider the -4/3, but -4 does. It fits within that interval -5 to -3. Now here's where it gets different than what we did in problem 2 when we're finding absolute extrema. We take whatever critical numbers that are in the interval and we take the actual endpoints of the interval and we plug them into the original function. So we find the value of the function y when x equals -4 and when x equals -5 and when x equals -3. So there's three values there. So when x equals -5, for example, if you plug in a -5 for all the x's, it comes out that y equals -3. When x equals -4, it would come out that y equals 2. And when x equals -3, it would come out that y equals -1. So we've plugged the two endpoints in, and then our critical number, we plugged each of those into the original function, not into the derivative, but into the original function. And now we consider these values. Whichever one's the highest is your absolute maximum. Whichever one is the smallest is your absolute minimum. So this one right here, y equal to 2, that's the highest value, so there's your absolute max. So absolute max is the point -4, 2. Now this point here, -3, that's the smallest value. That's going to be absolute minimum. That's the point -5, -3. All right, concavity is found with the second derivative. So we find the first derivative, and from that we can find a second derivative. And we can set that equal to 0. We get x equals 1/3. So we place it on a number line and we do a derivative test similar to what we did in section 3.2, but we're testing it into the second derivative. So if I choose a test point of 0 and a test point of +1, if I plug a 0 in here for that x, we get 0 minus 2. That's negative. If I plug in a 1 right here, I get 6 minus 2, it's positive. So this negative sign indicates that this interval would be a concave down interval. So it's concave down from negative infinity to 1/3. This positive sign indicates that this interval from 1/3 to infinity would be concave up. So from 1/3 to infinity, it's concave up. Okay, question 5 is also from section 3.3. Same as question 4. Point of diminishing returns really is just an inflection point. That's what we talked about in class. So to find inflection points, we determine concavity. So that means we need a first derivative. And then second derivative. And if we set that equal to 0, we get x equals 1. And that certainly fits within this constraint there. X is supposed to be, according to that, something between 0 and 5. And now we gotta just make sure that the concavity switches there, otherwise it's not a point of inflection. So when x equals 1, we can test 0, and we can test 2, and remember we're testing concavity, so it needs to go into the second derivative. So if we plug in a 0, we're going to get 0 plus 8 is positive. If we plug in a 2, we're going to get negative 16 plus 8. That's negative, so it's concave up, switches to concave down, so this is an inflection point. And it specifies here that x is the amount spent in thousands of dollars. So x doesn't equal $1, x equals $1,000. So $1,000 would be the point of diminishing returns. Okay. We've got a box we're trying to construct. So we have a 16 by 30 piece of cardboard. So I'm going to draw a rectangle. And we've got 30 inches by 16 inches. Now, what's going to happen is this employee is going to cut a square out of each corner, same size square. So these are going to be cut away. And then this flap here, this flap, that flap, and that flap, those are all going to be folded up to create a box with no top, an open top box. Now we don't know the size of these little squares that are going to be cut out, so I'm going to call it X, and because they're squares that are being cut out, they all have a length of X. So this distance then from here to here is 30 minus 2 of those x's that are cut out. And this distance from here to here, that distance right there is 16 minus the 2 x's that have been cut out. Now, the question here is, well, we need to create a box with the largest possible volume. In other words, they want a box with maximum volume. They want us to maximize volume. So this is an optimization problem. They've kind of hidden it in the fact that they don't actually use the word maximum, but they say the largest possible volume. So we need to maximize volume. Now, the volume of a box is length times width times height. And so we need to describe the length and the width and the height in terms of the same variable. So if the box were folded down flat, it wouldn't have any depth. It would just have a length of 30 and a width of 16. But if you fold these flaps up here, if you fold all four of those flaps up, then the volume of the box, the length of it would be 30 minus 2x. The width of it would be 16 minus 2x. And then once you fold the flaps up, now this box actually has a depth, and it has a depth that's the same as the length of those corners that were cut out. That would be the depth of that box. So or the height, I guess we've got the length times the width times the height right there. Those are the 3 dimensions of that 3-dimensional open top box. So in order to maximize volume like it asks, it means we need to take a derivative. I would not want to take a derivative of the expression as it now is, because you got a couple product rules going on there. So I'd go ahead and multiply those two together, or all three of those factors together. So multiplying this all out, we're going to have 4x cubed minus 92x squared plus 480x. Now if we do a derivative, then we would get 12x squared minus 184x plus 480. We can take a 4 out of that. And then set it equal to 0. And it turns out that this factors into 3x minus 10 and x minus 12. So we've got a couple values of x to consider. One of them here is x equals 10/3. Another one is x equals 12. We got to think about this. If x represents a piece of cardboard that's being cut out, if we cut out a 12-inch piece of cardboard on this side and on this side, that's not going to make sense because we only have 16 inches right there to work with. So for x to be 12 is way too big. That one doesn't make sense for the physical constraints of this problem. So the only critical value we need to worry about is x equals 10/3. Now we need to make sure that that would give us a maximum volume or a maximum value, so we do a quick little first derivative number line test. 10/3, we could test a value of 1, and we can test a value of 4. Remember, we're testing it into the first derivative. So if you plug in a 1, we're going to get a positive value. If we plug in a 4, we'd get a negative value. So that proves that 10/3 is a maximum. And it's asking, the question is, what size should the squares be in order to create a box with the largest possible volume? They're asking about what size of square should be cut out of each of the 4 corners. So the size of the squares should be 10/3 of an inch. 10/3 of an inch. Okay. So maximum profit. This is another optimization problem. We want a maximum profit, so that means we're going to have to take derivative of profit function. Now, profit is revenue minus cost. So first we need to determine revenue. Revenue is number of units multiplied by price. So we were given a price function of 200 minus x. So that's negative x squared plus 200x. So if we substitute that in for our revenue function here, then profit becomes negative x squared plus 200x. Now we subtract the cost function, each term of the cost function, so minus 20x minus 500. So our profit function, if we combine some like terms, so there's a profit function. If we use that now, take first derivative, we're going to have negative 2x plus 180. If we set that equal to 0, let's try some handwriting. We're going to end up with x equals 90. Got to remember though, this equals a number of units. They want to know what price will yield a maximum profit, not how many units. So the price, lowercase p, was equal to 200 minus x. So that's 200 minus 90. So the price is $110. Now it says when the profit is maximized, that means we're selling 90 units for $110. When the profit is maximized, what's the average cost per unit? So recall that average cost is cost divided by x. So the cost was 20x plus 500, and we divide that by x. And the x we use is the number of units which maximizes profit. That was 90. So 20 times 90 plus 500 over 90 is 25.56. Okay, question 8. For A, we need to find all the asymptotes. B and C, we've got some limits at infinity and infinite limits to evaluate. And then part D, there's a graph there. And to be honest with you, I'm going to start with, well, question 9 is not part D, it's another question. I think it'd be easier to answer question 9 and then go back and answer question 8. So the function from question 8 was 3x over x squared minus 9. That should say sketch the graph from question 8. So this is 3x over x minus 3, x plus 3. So the denominator is going to tell us our vertical asymptotes. We're going to have a vertical asymptote at x equals 3 and x equals negative 3. Now the horizontal asymptote is determined from the degree in the numerator compared to the degree in the denominator. We have a degree 1 in the numerator, but a degree 2 in the denominator. So what we talked about both in class and something that we learned last year in Math 1050 or whenever you took Math 1050 was that if the numerator has a lower degree than the denominator, then the horizontal asymptote is at 0. So we have the horizontal asymptote there. to know where the intercepts are. So to find a y-intercept, you let all of the x's equal 0. So a 0 here, a 0 there, and a 0 there. This is how we find an or a y-intercept, is to let all the x's equal 0. Well, that's going to give us 3 times 0, which is 0. And the 0 divided by anything in the denominator is going to be 0, so the y-intercept is 0. To find an x-intercept, you let y equal 0, or the whole function needs to equal 0. And we talked about this a few questions ago. If you have a rational function that's going to equal 0, then you solve for when the numerator equals 0. 3x equals 0 only when x equals 0. So the x-intercept is also 0, which is, again, right there at the origin. So that's the only intercept. Now, I'm going to consider what's happening on this area of the graph here to the right of that vertical asymptote. I'm going to test a few points. I'm going to test x equals 4. I'm going to test x equals 5, just to see where the function is. So if x equals 4, I'm going to get 12 over 1 times 7, 12 sevenths. So that's just a little bit more than 1. So when x equals 4, we're a little bit bigger than 1. If we do 5, so 5 times 3, that's 15. 5 minus 3 is 2. 5 plus 3 is 8. So 15 16ths, that's a little bit less than 1. So when x equals 5, we're a little bit less than 1. So what this is telling me is that piece of the graph there looks like that. Now I'm going to do a similar thing to find out what's happening on the graph over here in this region. So I'm going to test -4 and -5. So when 3 times -4 is -12. -4 minus 3 is -7. -4 plus 3, that's -1. So -12 divided by 7. A little bit more than -1, or in this case a little bit less, so that would be right there. If we test -5, we're going to have -15 over -5 minus 3, it's -8. -5 plus 3, -2, so -15 over 16 would be right about there. So that piece of the graph looking like that. Now I'm going to test a few points as we get closer and closer to that asymptote. So I'm going to test x equals 1 and x equals 2. If x equals 1, we're going to get 3. 1 minus 3 is -2. 1 plus 3 is 4. So 3 over -8. That's almost -1/2. And if I test 2, 3 times 2 is 6. 2 minus 3 is -1. So it's 6 over -5 when x equals 2. That's about right there. If I test -1, 3 times -1 is -3. -1 minus 3 is -4. -1 plus 3 is +2. So we get -3 over -8, that's 3/8. So that would be right about there. So what this is telling me is this piece of the graph is looking like that. Now, if you recall from question 8 wanted all the asymptotes, or at least 8a. So we have a vertical asymptote at -3, at +3, and we have a horizontal asymptote here at 0. So if we go back to question 8, vertical asymptotes where x equals 3, x equals -3, the horizontal asymptote, the line y equals 0. Now the limit as x approaches infinity of that same function, if we go back, x approaches infinity means we're moving along the x-axis here, and we're getting, the x values are getting larger and larger and larger. So x approaches infinity means the x values keep getting bigger and bigger and bigger. So here we have an x value of 4, here we have an x value of 5. Here we would have an x value of 6, 7, 8. So all of these x values are getting larger and larger towards infinity. The limit of the function as x approaches infinity is what is the y value approaching? Well, the y values are getting closer and closer and closer to our horizontal asymptote. So in this case, they're getting closer and closer to 0. Now part C, the limit as x approaches 3 from the negative direction. So as x approaches 3 from the negative direction, so here's where x equals 3, right here, and we're approaching from the negative. That means we're coming from this side, where I'm making this a little bit darker, so you can see as I'm approaching 3 from the negative side, the graph is going down to negative infinity. All right, question 10, we need average cost. So remember, average cost is cost over x, so we have there's the average cost. The average cost when x equals 100 is 2.35 times 100 plus 9,800 over 100. If you calculate that, we get 100.35. The average cost for 1,000 tons if we were to calculate that, so the idea here is to think about a trend. If we were to calculate the average cost for 1,000,000 tons and then for 1,000,000,000 tons and 1,000,000,000,000, it looks like the trend is the average cost is decreasing. Because it started out with an average cost for 100 tons, the average cost was $100.35. When we increased a ton to 1,000 tons, it decreased the average cost to $12.15. So you'd reason, well, if the number of tons keep going up, the average cost is going to keep going down. Well, does it keep going down indefinitely is the question. Or is it going to reach a point where it starts to level out? Determine the limit of the average cost function as x approaches infinity. So what they're wanting is the limit as x approaches infinity of the average cost function So what we're going to do is rearrange the function inside. So if there's multiple terms in the numerator, one single term in the denominator, remember we can break it up into several fractions. So 2.35x over x is just 2.35. And then plus 9,800 over x. Now, talked about this in class. If we have this kind of expression with a fixed numerator, but the denominator is increasing, getting larger and larger and larger, eventually we're going to have 9,800 over 10,000, and then 9,800 over a million, then 9,800 over a billion. So we have a relatively small numerator over a very, very large denominator, which means this fraction is going to get smaller and smaller and smaller, becoming closer and closer to 0. So when x does approach infinity, that fraction essentially disappears to 0, leaving us just that. So as the number of tonnage of recycling increases, the average cost is going to decrease and approach $2.35, but it's not going to get any lower than $2.35. In essence, $2.35 is an asymptote, a horizontal asymptote, at which the function approaches but never decreases below. Okay, question 11. We have from section 3.7, we need to figure out decreasing relative extrema. This is from section 3.1, 3.2, both of which we need to find a first derivative and set it equal to 0. So we'll go ahead and factor that quadratic expression. We get two critical numbers, x equals 1, x equals -1. Now to find out where it's decreasing and increasing, we test the first derivative, or test values in the first derivative. So I'm going to test -2, 0, +2. Remember, we're testing this into the first derivative because we want to figure out increasing or decreasing. Those are rates of change. First derivative tells us rates of change. So if you plug -2 into the first derivative for all the x's, -2 here, -2 there, we're going to get -2 minus 1, that's negative. -2 plus 1, it's also negative. Negative times a negative is a positive. If I plug in a 0 for both of those x's, we're going to get negative times a positive, which is a negative. If I plug in a 2 for both of those x's, we're going to get positive times positive, which is a positive. So this positive sign here indicates that this interval, the function's increasing, and also that positive sign indicates the same thing. So the function increases on the interval -infinity to -1, and also 1 to infinity. Similarly, it decreases on the interval -1 to 1. It also wants us to find extreme values. We can use the same test here, the first derivative test. Right here we got to switch from increasing to decreasing. That means the function increases to a high point and then decreases after that. So we know that there's a relative max when x equals -1, and then there's a relative min when x equals +1. If we plug a -1 into the function, we'd get -1 plus 3 plus 2. That's going to give us 4. And if we plug a 1 into the function, we're going to have 1 minus 3 plus 2, which is 0. Concavity and inflection points is second derivative. And if we set that equal to 0, we're going to get that x equals 0. So to find concavity, we do a test into the second derivative. So I'm going to test -1, +1. We're going to get 6 times -1, that's negative. 6 times +1, that's positive. So that positive negative tells us that the graph is concave down from -infinity to 0, concave up from 0 to infinity. And then because it switches concavity, we know we have an inflection point or a point of inflection at the point 0. Then you go back all the way to the original function. If you plug in a 0 for all the x's, you're going to get a 2. So the inflection point is a point 0, comma 2. So we can start plotting some of these on our graph. Negative 1, comma 4 was our relative max. 1, comma 0 was our relative min. We had an inflection point at 0, comma 2. Part C, we need to sketch the function. That includes zeros. So that's why the factored form of the function is given, so we can find the zeros. We know that there's one at negative 2. So there's a 0 at negative 2. And there's also a 0 here at positive 1. Now this particular 0 has multiplicity because of the exponent. The multiplicity is even. We talked about this in class. You also learned this in Math 1050 class. When the multiplicity of the factor is even, that means that the 0 bounces. So right here when x equals 1, the graph's going to bounce off rather than cross through. Now we also consider the degree of the polynomial. This is y equals x to the third, and it's a positive leading coefficient. So the end behavior of a x to the third polynomial with a positive leading coefficient means the left side is going down, the right side is going up. So as we try to connect these two, we cross through that x-axis because that has a multiplicity that's odd. This is a relative maximum, so it comes back down once it reaches that point, bounces there, and it's also a relative minimum. So we had the intercepts, we labeled the maximum, there's the minimum, there's the point of inflection. We've answered everything that's been asked. So question 12 is from section 3.7. They're wanting us to conceptually analyze the difference here between a graph that represents the graph of a first derivative and what a possible actual function might look like. Now, this first derivative graph, this part that I'm highlighting, is negative because it's below the x-axis. So if we were to do a number line test similar to what we've been doing when we're finding extrema, the first derivative is 0 right there when x equals negative 1. So we would say the negative 1 is a critical value, and it's a negative to the left of it. This interval right here, because it's above the x-axis, it's positive. So if we were to evaluate this from a question in 3.1 or 3.2, where we were finding intervals of increase or decrease or relative extreme, we would say that the function decreases when it gets to negative 1, and then it starts to increase. So we need to think of a function now that would decrease to a certain point and then increase after that. And we've seen lots of examples of a function like this that decreases to a certain point and then increases. It needs to have one relative extreme at negative 1, and in this case it can be a minimum value. So for example, if we have negative 1 as a minimum value, we have a function that decreases and then increases. So we're talking really about a parabola.